All right, students. So we'll continue from where we left last time. This is the second part of 12 Feb March 2025 paper 9701. So question number 21, it states river water in an agriculture area contains these ions. This water is treated with a calculated quantity of calcium hydroxide. What is precipitated from the river water when calcium hydroxide is added? So basically, we have to understand the formation of a precipitate, that means a formation of a solid compound by the reaction of the calcium hydroxide with one of these ions. So let's start with the ammonium. If there is a reaction between calcium hydroxide and the ammonium ions, then there shall be a formation of calcium hydroxide and ammonia gas and water. But here, there is no such thing as solid. Calcium hydroxide is it should be ammonium hydroxide, a slight mistake. There shall be a formation of ammonia gas. Yes, there is formation of the ammonia gas in this case, and if there was some sort of the negative part mentioned here, let's suppose chlorine, then it would have produced a calcium chloride whatsoever. Since nothing is mentioned along with the ammonium ion, so we do not write any part here, but it will stay as calcium ion. So it is basically no such thing as solid compound here. Along with that, there is formation of water. So no solid compound is formed. Now we check the uh, hydrogen carbonate. So hydrogen carbonate will be when reacting with the calcium hydroxide will produce calcium hydrogen carbonate, CaHCO3 whole twice. Now this compound is basically water soluble. It is soluble compound. It is not insoluble. It is a soluble compound, said as so it doesn't form any precipitate. With the chloride, the calcium hydroxide will produce calcium chloride. Now, chlorides of all the group 2 elements are also soluble, so it is soluble compound. Nitrate, so calcium nitrate is also soluble here. So all of these are basically soluble. But what about the carbonate? So you know that calcium carbonate is a solid compound. It is solid, that's why we call it as marble. We call it as chips, limestone, whatsoever you know about it. So this compound is solid compound. That's why there will be a formation of the precipitate when calcium hydroxide reacts with the carbonate ion. So that's why the correct option becomes the B option. Now, next question number 22. 4 atmospheric pollutants are listed, and we have these 4 different oxides present. Then it says which pair of the pollutants react to form peroxyethyl nitrate PAN. So this is a pollutant which is included in our syllabus in 2022 and onwards. Before that, it was not a part of the syllabus. Okay, so now how do we get a formation of the PAN from these oxides, from these atmospheric pollutants? These are all basically considered as primary pollutants. These are all primary pollutants which are directly produced from one or the other sources, whereas PAN is considered to be a secondary pollutant, which is basically produced by the combination of these pollutants. So when primary pollutants react with each other, they produce a secondary pollutant. So for this purpose, I will go through my notes of AS chemistry to find the answer. All right, so here in my notes, you can see the formation of the pan. So pan is here mentioned CH3, C triple O, and O2. This is pan. Now this is formed by the for reaction of the hydrocarbons. The other name of hydrocarbons is VOC, volatile organic compounds, in the presence of the sunlight and in the presence of oxygen along with nitrogen dioxide and O2. So this is how we get the formation of pan. So basically, this happened during the daylight. One way of reaction was that, and the other reaction is mentioned here. Nitrogen oxide react with VOC. VOC is basically other name of the unburned hydrocarbons. Basically, they are small organic compounds. They are small hydrocarbon chains. These are hydrocarbon chains, but they are not burned, unburnt hydrocarbons. They react in the presence of the sunlight and oxygen to make the pan. All right, now we go back to the question. The questions had these options. So we do require the nitrogen oxide. It could be NO, it could be NO2. And we also required unburned hydrocarbons, or you can also call it as VOCs. So these two are required, 1 and 3. So 1 and 3 mentioned here. That's why the correct option becomes option A. Now, next question, number 23. Which graph describes a trend found in group 17? So group 17 is basically the group of halogen elements. So here we have option A. It says bond length in X2 decreases from chlorine to iodine. So basically it's wrong. We know that chlorine is smaller than bromine. If it is slight size of this, if it is left size of the chlorine, then bromine would be a larger size, and iodine will be even more larger in size. So bond length is basically the distance between the two halogen atoms from nucleus to nucleus. From nucleus to nucleus, that distance is called bond length. So whenever we have two chlorine atoms uh, bonded through covalent bond with each other, then that will be a bond length. So as we increase the size, then the bond length will increase. So that's why this A is incorrect option. C says boiling point of X2 decreases from chlorine to iodine. So we know that that's also wrong, as the intermolecular forces are stronger in case of the iodine. Iodine has the strongest ID forces, or you can say the instantaneous dipole forces or London forces, whereas chlorine has the weakest within this group of elements. It is weakest identity forces. So considering that the chlorine will have the lowest boiling point, that's why it is in the form of the gas state, and iodine is in the solid form at room temperature and pressure. That's why C is wrong. Now, option D says bond energy of HX. Now, bond energy is basically associated um, with the extent of overlapping between the hydrogen atom and the halogen atom. So, if the size of the iodine is greatest, then it will have very small overlapping with the hydrogen atom, and there will be large distance between them. So greater the bond distance, smaller the bond energy. Bond energy is inversely proportional to the bond length. It is inversely proportional to the bond length. We write like this: bond energy is inversely proportional to bond length. So hydrogen iodide does not have a high bond energy. Instead, it has the lowest bond energy because it has the longest bond length. So that's why D is wrong. Now, if you check B option, then strength over double forces. So yes, bond strength are van der Waals forces means here the IDID forces, or in other words, it is called as intermolecular forces. So intermolecular forces are strongest in case of iodine because of its the greatest number of electrons. It has the highest electrons in its atom as compared to bromine and chlorine. Highest electrons, the greater the number of electrons, the greater will be the strength of the van der Waals forces or the IDID forces. So that's why B is the correct option. Now the next question, number 24. Gas M is produced when ammonium chloride is heated with calcium oxide. Which row is correct? All right, here we have to decide the type of the reaction and the identity of the product M, which is a gas. So for this purpose, I will again show you my notes on which you can find all the answers. So here in my notes, the topic is basically the displacement reactions of the ammonium salts. Now here we can see that the salt of the ammonium ion, when reacting with the calcium hydroxide, will produce the salt, which is calcium chloride plus ammonia and water. Here, the ammonium ion is acting as an acid and the hydroxide is acting as a base. So if we have the calcium oxide, that will still be considered as a base because of its nature. And the type the gas produced is only the ammonia gas, which is produced here. So we can apply this concept in our question. We can have uh, a reaction with any type of the base reacting with the salt with ammonium ion. So when the reaction is there, it is the acid-base reaction. So yes, acid-base reaction, and the identity of M, which is a gas, is basically the ammonia gas. So considering that, the correct option becomes a C option. Now the next question, question number 25. This question says two nitrates decompose on heating according to the equations shown. So we have these two equations. And the is decomposition of lead nitrate into lead oxide, nitrogen dioxide, oxygen, and ammonium nitrate decomposes to nitrogen plus oxygen and water. 1 mole of each nitrate is heated separately. The gas produced in each reaction is bubbled through NaOH. The volume of the gas does not react with NaOH, is then collected and measured, which nitrate produces the greater percentage loss in mass and produces the greater volume of gas collected. All right, now here in this question, we are supposed to do some calculations. Only then we'll be able to answer the question. Now, first of all, if it says greater loss of mass, greater percentage loss of mass, then it means that the initial reactant has lost some of the mass. And how do we know? Basically, we are, let's suppose, using an electric weight machine or electronic balance. The electronic balance will be able to measure the mass of the products as well when it was completely decomposed. Since they are decomposed completely, which means it has been totally decomposed, and whatsoever mass of this compound was initially, it should be checked or compared with the masses of all these three products. But the problem here is that all the three products are not in this solid form. There are two in the gaseous form and one in the solid form, which means that these two gases will escape out of the system. So when they will escape out of the system, the mass of only PbO will be there to be measured, and electronic balance will only be able to calculate the mass of this solid compound. And similarly for the second reaction, the electronic balance initially calculated some mass of the ammonium nitrate, and when the reaction was done completely, it would be able to only calculate the mass of the water as a liquid. It is still there in the system because it could not be evaporated or escape into the system. Only these two gases would evaporate in the form of the gases, or they would escape out in the form of the gases. So that's how we have to uh, idealize, or we have to do the strategy to find out the answer. Now, for this purpose, we have to look into this important point here, 1 mole, which means the mole or stoichiometry method is to be applied here to find the answer. The mole could be converted into the molar masses. So molar masses of all these reactants and products must be calculated, only then we'll be able to answer. So first of all, we'll first calculate the MR value of this whole compound lead nitrate. So MR value will be calculated for this compound. So if you use the periodic table, you will be able to answer, since the value of lead is basically the value of that is 207.2 AR value. The AR value of that is 207.2. For nitrogen, it is 14. For oxygen, it is 16. So after doing the required calculations, you have to do like this. As you know, MR can easily be calculated by considering all the masses. So MR value of that nitrate is basically 455.2. You have to consider the multiple of 2 as well. You have to multiply 2 with the mass of the lead nitrate. Only then you will get this value of 4.455.2. Now on the product side, the mass of the gas, you do not need to check the mass of the solid, because we have to consider the loss. So basically, loss in mass can be calculated only by calculating the MR values of the nitrogen dioxide and MR value of the oxygen. You do not need the mass of lead oxide here. All right. Okay, so for nitrogen dioxide, it will be like 4 times the mass of the NO2. That's how you calculate the MR value of this. So when you do the calculation, the mass of NO2 will come out to be 182, and the mass of oxygen is 32. Okay, now I have calculated the masses of the gases and the mass of the initial reactant. Now I need to calculate the total mass of the gas which is evolved out. So 182 plus 32 would give me 216. Now that's the mass of the gas which is released. Now I have to calculate the percentage. The percentage loss. For this purpose, I will take the mass of the gas in the numerator, 216, divided by the mass of the compound initially. Keep in mind that I have multiplied this 2 with the mass of lead nitrate. So 455.2 into 100. Now this will give me answer of 47.45%. The answer is 47.45%. Now that's the mass of the loss in percentage loss in mass. Now for second reaction, I do the same way. The MR value of ammonium nitrate is basically 160. Simple, add the AR values of all the atoms of all the elements. Now I have to calculate the mass of the nitrogen gas. So this nitrogen gas, when multiplied with this mole ratio 2 as well, the mole, it's mole R2, so it will give me 56. So 56 for nitrogen, and for oxygen it is 32. Now add these two gases. We do not calculate the mass of the water since it is a liquid form. Okay, now 56 plus 32 is now equal to 88. Now calculate the percentage loss in mass. That is equal to 88 divided by 160 into 100. The answer will come out to be 55%. Now you can see clearly here that this time the mass percentage loss in mass is higher in second reaction as compared to first reaction. So from here we will stick in front of the ammonium nitrate because it has a greater percentage loss of mass. Now the next part column says greater volume of the gas collected. Now it says gas collected. Now which gas will be collected? It will be that gas which does not react with the sodium hydroxide. So if we look in first equation, then we know that there are two gases, oxygen gas and nitrogen dioxide gas. Nitrogen dioxide is basically an acidic gas because of the non-metallic character of the nitrogen. So it is an acidic gas and it can definitely react with the sodium hydroxide since it is a base. So there will be a sort of reaction between the nitrogen dioxide and NaOH. So that cannot be collected. So we are only left with the oxygen gas. So this will be collected, and in the second equation, we have two gases, the nitrogen and the oxygen gas. Now, nitrogen is, a very inert gas, almost 78 to 79% in atmosphere. And we do inhale this gas in our body, but that does not react with our body. They do not take part in chemical reaction because of very strong triple covalent bond within the nitrogen molecule. So because of this triple covalent bond, it is considered to be inert gas. So this cannot react with the NaOH. So no reaction with NaOH as well as the reaction of O2. Yeah, what about the O2 in the first case? O2 is basically a neutral gas. So it is not considered to be acidic or basic. It is totally a neutral gas. So oxygen gas will not be reacting with the NaOH because NaOH is a base, so it has to react with the acidic gas. Since O2 is not acidic or basic gas, so that will only remain as such. So both the reactions O2 will be collected. So O2 will be collected in both the cases as well as N2 will be collected in the second case. All right, now in the first equation, we have only one gas. Now the mass of that gas is 32. In the second case, there are two gases, the nitrogen whose mass is 56 and the oxygen whose mass is 32. So if you look at here, the mass of 56 plus 33 is 88 gram and the mass of oxygen is only 32. That means that greater volume of gas is collected in the second case. So the gas in the second case will be greater in volume because there's more mass of the gas collected. It is 88 gram in the second equation and it's just 32 gram in the first case. So we know that the ammonium nitrate will produce more amount of the gas collected. So considering that, the only option becomes A option as a correct answer. Now the next question, number 26. Organic compound X has an empirical formula C2H4O. Compound X is reduced by lithium aluminum hydride, but not the NaClO4. What is compound X? Okay, if you remember from the knowledge that LiAlH4 is stronger reducing agent as compared to the NaBH4, which is comparatively weaker reducing agent. So we have to consider and decide which of these compounds will be reduced by LiAlH4 and not by NaBH4, and also that it should be the compound which must be related with the empirical formula. Ethanoic acid is the compound which can be reduced by LiAlH4, but not by NH4. But the thing is that ethanoic acid cannot be considered to be the empirical formula since it is already in its it is already in its uh, actual formula. If we consider its molecular formula, it will be C2H4 and O2. So it is basically the molecular formula and its empirical formula will be, that's the molecular formula, and its empirical formula will be CHO. So CHO is the empirical formula of ethanoic acid. So it cannot be the compound. Ethanol, on the other hand, is aldehyde. It cannot be, it is not the one which can only be reduced by NaBH4. So aldehyde can be reduced by both NaBH4 and LiAlH4, and also that's all about it. So B is not the option. So it can be reduced by both. It can be reduced by both. Butanol is already the reduced form. It does not require any further reduction. It is already reduced form because carboxylic acid are reduced to aldehyde or ketone, and aldehydes are further reduced to alcohols. So carboxylic acids are first reduced to aldehydes or ketones, depending upon the structure, and the aldehydes are further reduced to the alcohols. So that's why C is not the option. Now butanoic acid. Butanoic acid is basically CH3, CH2, CH2, and COOH. Now that's its structure formula. We now deduce its molecular formula. So molecular formula would be C4 and H8. If you calculate 3, 5, 7, and 8. 8 hydrogen atoms and oxygen atoms are 2. Now that's its molecular formula. Now its empirical formula would be C, C2, H4, and O. That's the same empirical formula which you will see over here. So this is the real compound which can only be reduced by the LiAH4 and not by the NaBH4. So that's why the correct option becomes the D option. Now question number 27. What is the mechanism of the reaction of hydrogen cyanide with propanol? Okay, so to decide what kind of mechanism is it, we have to look into the literature. So I will show you my notes. And these are my notes of the AS chemistry, which you can demand or request to get access of from comment section, or you can approach me, or you can reach me out on WhatsApp or Instagram. Okay, within the topic of the carbonyl compounds, which is aldehydes and ketones, we can see the reaction with the HCN, and that is basically the nucleophilic addition reaction. And you can see clearly here in the mechanism step mentioned over here how the reaction was done. So initially the nucleophile is added into the carbocation part, or you can say the positive sigma positive carbon of the carbonyl group in the first step, and as a result, the oxygen gets a negative charge that will now attract the hydrogen of the HCN to produce the OH group. So this is how we decide that this is a nucleophilic addition reaction, since this is a nucleophile and it is being added into this because there is no removal or substitution part here. So that's basically the addition of the nucleophile into the compound. So this considering that, the correct option becomes the option number C, which is nucleophilic addition reaction. Now, question number 20 may be synthesized from an alkene with the formula this by an addition reaction. And we have these 40 compounds now. Okay, so considering the reaction with an alkene with the definitely bromine molecule, the addition should be with the bromine Br2 molecule that can only give you dibromo compounds of all these types. Now, which of the alkene would be the one having this formula, molecular formula? So I can suggest these structures. We can have a double bond at position number carbon 1 and 2, or we could have a double bond between carbon second and third, because these are the only two isomers which we can consider here of the butene. or one more could be the one in which the carbon first and second had double bond, and then this carbon bonded with one below carbon and one above carbon. So here we have now the three types of the isomers with the molecular formula of C4H8. 1, 2, and 3. Okay, now we have to relate the structure with that of the uh, A, B, C, D structure. So I'm going to draw simple versions of the structure to get an idea. One dibutane will be like this. There will be 4 carbon atoms, and 2 bromine atoms will be present on carbon number 1. I can give this carbon as 1, or I can give this carbon 1, both are same. So I'm gonna put the bromine atoms on the rightmost carbon atom, one above bromine and one below bromine. These lines indicate that bromine atoms are attached on this carbon. Okay, in B option, the compound would look like this. 4 carbon atom with bromine on position number 1 and 2. So in this case, I'm going to put from left position. So this is carbon number 1 with bromine, and this is carbon number 2 with bromine. Now option C says 4 carbon atoms with position 1 and 3. Now in this case, I'm gonna put from from right. This is 1 and this is third carbon atom. For option D, I need some space to draw the structure. It should look like this. Carbon, we have the carbon, and another carbon along with carbon the center. Now bromine will be attached on position number 1 and position number 3 carbon atoms like this. Okay. Now we have to relate these 3 isomers. If we have the addition of the bromine on isomer number 2, then I should get one bromine over here, another bromine over here. What I can see here that this structure matches with the option B. We have bromine on position number 1 and 2. And for isomer 3, the bromine should go on position number 2 and 3. Position 2 and 3 should have bromine, but there is no such structure in position 2 and 3 are occupied with the bromine. So it's not the isomer 3, definitely. And isomer 1 is the one in which this carbon is already saturated with all the 4 bonds, so it cannot give any other addition reaction. It has all the bonds completed. All 4 bonds are there, so it cannot give the reaction. So only isomer is 2, which will give the option B as a correct answer by the addition of the bromine on this isomer. Question number 29. The structure of compound G is shown, and we have this compound over here. Compound G undergoes addition polymerization. This diagram shows the repeat unit of the polymer formed. Okay, so here it says that the reaction is of addition polymerization, which we already familiar with that on the alkene types of the polymers will give this type of the addition polymerization, which involves carbon-carbon double bond. So they are joined with other monomers of the similar type to give one large molecule as a polymer. So here in this compound G, the carbon-carbon double bond is present over here, which means this is the portion which must be added with the other similar position of the other monomers to give a polymer. So it means that we can consider that a dangling bond should be here and one dangling bond should be here, and this bond should convert into a single bond. Or you can say the continuous bonds are on the either sides and single bond is there. The rest of the part, this portion will be present as a side group or substituent, and this should also present as a substituent. So we can see that in option A, the C2 bond and is there, but carbon to carbon double bond is double bond here, which should not be there. That's incorrect. And also this bond should not be the continuation bond. So it is also incorrect. In option B, again C double bonded and is represented as a continuation bond. That is incorrect. And carbon to carbon double bond is there. That is also incorrect. It should be a single bond. But C double O2 C that is a correct portion that is not involved in polymerization. In option D, C double bond and is there. That is incorrect. C to C bond is there. That is also incorrect. And then this portion is correct in a sense that it is not involved in polymerization. And C option, C triple bond and is there as a side group, and this ester part is there as a side group, and the carbon to carbon bond is present as single. That is also correct. So that's why the correct option becomes the C option. Now, question number 30. Compound T is tested with 3 reagents and gives results as shown. Which is compound? What is compound T? Okay, here we have to discuss the functional group of the compound by looking into the observations and the test results. All right, so it says that when reagents 2 for D and pH, it gives pollen precipitate. Now we remember from the literature that this test is giving the positive test only with the aldehyde and ketone. So aldehyde should be there and ketone should be there. The compound should only give result with the aldehyde and ketone. Failing solution gives no reaction, which means that aldehyde is not there because this test is given by the aldehyde only. So which means aldehyde is not there. That means that ketone could be there because ketone does not give reaction with the failing solution. And acidified K2CO7 says no reaction, which means uh, it could not be aldehyde because aldehyde can be further oxidized by using K2. CO2 separation diachromate can give reaction. So it is not there. Whereas ketone cannot give this reaction with the potassium dichromate, so ketone would be there. Now we have these different possibilities. Now we check the options. Option says A says that it has the aldehyde group present here. But in our observations, aldehyde is not there according to the second row and according to the third row. So it is not the correct option. The option B says it is alcohol. This is not alcohol. So alcohol cannot be there because in our case, there is only aldehyde and ketone. One of these two means only ketone is there, but not the alcohol. There is no mentioning of the alcohol here. So it is not correct. C option says that it has two groups. It has the alcohol group and it has a ketone group. So ketone group is right, but not the alcohol group. It would not be there. So that's also incorrect. Now D option says it contains only one functional group, that is a ketone group. So yes, ketone group is a compound which can give all these three positive results. So that's why the correct option becomes the D option. Now the next question is question number 31. Reagent X is added separately to 2-methyl-butene-1-ol and 3-methyl-butene-2-ol. The visible results are different. What is reagent X? Okay, so here in this question, we have to focus on the reaction of these four different reagents with these two compounds, and as a result of which the product should that should be produced should be different for these two reactions. So we'll separately discuss the reactions. I'm going to draw the structure of 2-methyl-butene-1-ol first. This structure is basically like this in a simplified form. We have 4 carbon atoms, and in these 4 carbon atoms, there is methyl group on second carbon atom, and uh, there is OH group on the first carbon atom. So OH is on first carbon atom. So this is the structure of 2-methyl-butene-1-ol. I'm going to label it compound A. Now the compound B, which is 3-methyl-butene-2-ol, would look like this. We have 4 carbon atoms again, and then methyl group is on carbon number 3 from left side, and alcohol group is on the carbon number 2 from the left side. So this is the structure of compound B. Now we react these two compounds separately with these four reagents. So starting from Na, sodium. So sodium can give reaction with the alcohol, and both of these are alcohols. This one is primary alcohol, and this one is secondary alcohol. All right. Now sodium can react with both. So A and B both can give reaction. So there is no different results in this case. Compound now reagent B, which sorry, C, PCl5. PCl5 will react with the both alcohols in a nucleophilic substitution reaction. So nucleophilic substitution reaction is there with PCl5. So which means both compound A and B can give the reaction. So there is no difference between them. D says acidified KMnO4. Then this is used for the oxidation of alcohols into the respective aldehyde or ketone. So primary alcohol will be oxidized into aldehyde and further into the carboxylic acid. And that the compound B will convert it first into the ketone and then no further reaction. There will be no further reaction of ketone with the KMnO4. So, but first reaction is possible for both the cases. That's why we cannot differentiate on the basis of acidified KMnO4. So both reaction A and B can give. Whereas alkaline I2 is basically reaction of triiodomethane or iodomethane test, in which CHI3 is produced in the form of yellow PPT. So for this reaction to be possible, we need to have a compound in which methyl group is bonded with carbon having OH group on it in case of alcohol, and then a hydrogen on it. Or in case of the aldehyde or ketone, it should have a group like this, CH3 bonded with a carbonyl group directly. And then we have another substituent over here along with the hydrogen at this point. Now, if we look at option compound A, then we do not see this part CH3OH because this is CH3CH2 and this is CH2OH. So A cannot give this reaction with alkaline I2. However, the compound B does contain this group. We have CH3 and then CHOH part present over here, which totally resemble with this part. So this part is present, which means this can give reaction with the alkaline I2. So that's why B is the correct option. Now the question number 32. Compound Y is hydrolyzed by aqueous silver nitrate from the precipitate that is soluble in dilute aqueous ammonia. Compound Y undergoes an elimination reaction to form an alkene. What is the skeleton form of compound Y? Okay, we have now 2 points to find out the real structure from the given option. The first point states that the reaction with silver nitrate will produce precipitate that is soluble in dilute aqueous ammonia. We remember that iodine, if they if it is the iodohaloalkane, it is the iodoalkane, then iodoalkane like this are bonded with iodine, then it will produce the yellow PPT, and that cannot be soluble by dilute or concentrated ammonia. It cannot dissolve that iodine precipitate, so it will definitely not be iodine. And for bromine, it can be diluted by concentrated ammonia. Concentrated ammonia can dilute the bromine. But chlorine, it can be soluble by both the dilute as well as concentrated ammonia. So dilute aqueous ammonia means it can dissolve the chlorine precipitate. So that's why the the compound which is going to be figured out should contain chlorine because chlorine can be diluted, can be dissolved. Sorry, it can be dissolved by using the dilute aqueous ammonia. So that's one of these two, which means A and B are incorrect. The second point says compound Y undergoes an elimination reaction to form an alkene. Now we have to decide which of these two will give the elimination reaction. Elimination reaction means we have to eliminate the definitely a chlorine to make an alkene. We will not go for the removal of two hydrogen atoms to make alkene. Instead, we will see how this chlorine can be eliminated here. So chlorine will be eliminated from this carbon and the hydrogen will be eliminated from the adjacent carbon. So these two will be removed from here and as a result of this, a double bond will form between these two carbon atoms. Whereas in case of D, this chlorine will definitely be removed, but with this carbon, the adjacent carbon is this one which is present at the center. This carbon does not have any hydrogen. There is no hydrogen on it. So definitely if there is no hydrogen, then it cannot be removed, which means no double bond can be formed over here. So that's why we can expect that that's only option C, which can give the required observations. Now, question number 33. Propane 2-ol can be converted into 2-chloropropane using reagent M followed by reagent N. Which way is correct? All right, so here we have to decide the proper pathway of the reaction, a sequence of reaction which can lead to the formation of the 2-chloropropane by these two reagents. So first I need to represent these two structure in a simplified form. This is propane 2-ol having OH on the second carbon, and this is 2-chloropropane having chlorine on the central carbon like this. All right, now we have to decide that this propane tool must react with one of these four reagents, and in fact, there are only three different ones. This one is concentrated NaOH. Now, concentrated NaOH will not show any kind of reaction with propane 2O. So there is no reaction with NaOH. But a reaction with the concentrated sulfuric acid or phosphoric acid will definitely cause the dehydration reaction. As we know that concentrated acids like this H2SO4 or phosphoric acid, they both can lead to dehydration, which means this secondary alcohol will go by dehydration reaction, which will involve removal of water. So a hydrogen atom of the adjacent carbon will be removed along with the OH. So I can expect that this OH is removed from here and hydrogen is removed from either the right carbon or the left. Both means same here. So when they will be removed, the compound that will produce will look like this, having double bond over here. Now this is propene form here. Now this must be reacted with the reagent N to make the compound 2-chloropropane. So what do you expect here that if we add with Cl2, then Cl2 will add our both the carbon atom of the double bond and this double bond will convert to single bond. But this is not our required compound. We will not get the required compound over here, which means this is not the right reagent. Instead, the right reagent is the one in which HCl is added. So when HCl is reacted with this reagent and then we can have the two ways. Either you can go with the Markovnikov addition or rule, and you can go with the anti-Markovnikov. Markovnikov says that the hydrogen will go on this hydrogen, the one having more number of hydrogen atoms. So hydrogen will add over this and chlorine will be added on this compound. So Markovnikov will show this compound which is a required compound. So hydrogen is added on this carbon, on the right carbon, and chlorine is added on the central carbon. And that's how you get a single bond between them. So this is the 2-chloropropane. So which means that the HCl is added in the product form as a result of the phosphorylation, which means that the correct option becomes the C option, having 2 ticks in a row. Now, question number 34. Skeletal formulae of 4 organic compounds are shown. 1, 2, 3, 4 other compounds. Which two compounds, when separately heated with sulfuric acid, produce propanoic acid as one of the products? All right, so here we have to discuss the reaction between these 4 compounds with the dilute sulfuric acid, H2SO4. The first compound is basically the propanol. Now, reaction of propanol with dilute sulfuric acid is not studied in our syllabus, so there is no such reaction. So, as a result of this, we will say that the uh, the first compound is not the one which is going to react with the sulfuric acid, because it is not the oxidizing agent over here. It is not working as an oxidizing agent here to oxidize propanol. We should have the KMnO4 or K2Cr2O7 as the oxidizing agent to oxidize the propanol into the carboxylic acid. So that's why it is not the right option. The compound 2 states this ester compound. So dilute sulfuric acid go with a hydrolysis reaction with the ester compound. This is ester. So ester will go through hydrolysis. It is the hydrolysis reaction. And as a result of this, it is split into 2 parts, the carboxylic acid part and the alcoholic part. Now this part which connected with oxygen to a single bond will convert to alcohol. And since there are 2 carbon atoms, it will convert into the ethanol. And the other part containing 3 carbon atoms, 1, 2, 3, this part will convert into the propanoic acid, which is bonded with the carbonyl group. So this is propanoic acid. Now, compound 3, it is the nitrile group. So nitrile group basically converts into the carboxylic acid by the reaction with the dilute sulfuric acid. So, yes, this C will remain there, but it will convert into the propanoic acid because there are 3 carbon atoms over here. In compound 4, the same is the ester compound, so it will convert into alcohol and carboxylic acid. So this portion will convert into propanol because it is connected through simple covalent bond with O. So propanol is produced here, and this group containing 2 carbon atoms will convert to ethanoic acid. So in this way, we do not have any propanoic acid, which means the only 2 compounds containing propanoic acid is compound 2, and then we have the propanoic acid in compound 3. So 2 and 3 are the correct options, that was C is the correct answer. Now question number 35. Question 35 shows states 1 chlorofluoropropane and 2 bromotoluene react separately with aqueous nitrate in ethanol. Both reactions proceed by Nucleophilic substitution and precipitate is formed. The time taken for first compound is T1, time taken for second compound is T2, what is 3. All right, here we have to elaborate this reaction. For the compound first, which is this one chloro2-methylpropane, I need to draw the structure. It would look like 3 carbon atoms. And on carbon number 2, we have the methyl group. And on carbon number 1, we have the chlorine. So chlorine on carbon number 1. And second compound is 2-bromo-2-methyl butane. So it will look like this structure. Carbon, again, there, now this time there will be 4 carbon atoms in a straight chain. On carbon number 2, we have bromine. And on carbon number 2, again, we have methyl group like this. All right, so this is the structure of the second compound. Now, on the basis of this structure, we have to decide what kind of reaction will be given by them. Since this says it is a nucleophilic substitution reaction, then we have to look into the literature back to understand this. We have SN1 and SN2. We remember that the primary haloalkanes. The primary haloalkanes basically give the SN2 reaction, whereas the tertiary haloalkanes provide the SN1 reaction. So tertiary haloalkane have SN1 mechanism in which in which two steps are there. First step involves the removal of the halogen and fast step, and second step involves the addition of the nucleophile to the slow step. So we can now look at the structure. The first structure has chlorine on carbon 1, which is bonded with only one more alkyl chain. This whole is considered as one alkyl chain. So that means it is a primary halogen. It is a primary one. And this second compound has bromine, which is bonded with three alkyl groups over here. This means it is a tertiary halogen. So primary is the one which goes with the SN2. So it should go with SN2. So the compound which contains chlorine, this is the primary. So it should go with SN2. So chlorine is here, chlorine is here. So it will go with the SN2. And the one which contains bromine is a tertiary halocane, and tertiary halocane goes with SN1. So bromine compound should go SN with SN1. So these two are the correct options from here. Now the next part is about the time taken. The time for the precipitate to form. Okay, so in first compound, there is a chlorine bonded with a carbon, and in second case, we have bromine bonded with a carbon. Now we again look into the literature that the reaction in which the precipitate is formed with the aqueous silver nitrate means that the carbon to hydrogen bond must be broken. So carbon to chlorine bond must be broken to make the AgCl precipitate. The precipitate is that of the silver halide, so AgCl and AgBr. So carbon to bromine, carbon to bromine. Now we know that the bromine atom is larger in size as compared to chlorine. And as a result of this, the bond length in carbon to bromine is greater as compared to bond length in CCl. So CCl bond length is smaller than CBr bond, which means that it is easier to break the bond of bromine. So when this bond can easily be broken as compared to Cl, then it will quickly react. So the reaction will be quicker in case of the CBr, which means the time taken should be smaller for the precipitate to form. The precipitate because of the reaction with the silver to make the silver halide. So we can say that T1 is going for the chlorine. So T1 is allotted to this compound and T2 is given to the one which has bromine. So BR time should be smaller. It should be smaller. The BR time is basically T2 time. So we can say that T2 time, the time taken for the precipitate to form should be smaller, which means it is giving a quicker reaction. So T2 must be T2 time is smaller than T1 time. Again, that T2 is for bromine and bromine to carbon bond is broken easily since the bond length is greater and bond energy is smaller. Bond energy is smaller in case of the carbon to bromine bond. That's why. So bond energy is smaller and bond length is greater for CBr bond. So we look at here that T1 is greater than T2 is the inverse of T2 less than T1. So T1 is greater than T2. So we have T1 greater than T2 in option B and D. So the only row with 2 ticks is the option B, in which 2 ticks are there. So that's the correct answer, option B. Now question number 36. The diagram shows the structure of progesterone. Which statement about progesterone is correct? So we have these 4 options. So we have to validate the correct option from the given structure. We can see the molecular formula. There are of two types. The one containing carbon 19 and the other one carbon 21. So we first check how many carbon atoms are there. So I'm going to number the carbon atoms here to make it easier to count the number of carbons. So this is 1, 2, 3, 4, 5, and 6. This is 7, 8, 9, 10, 11. This is 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So they are 21 carbon atoms in this compound, which means the correct option should become the carbon number 21. So B and D are correct ones. Now we need to check the second point of this compound, that is about the chiral carbon atoms. So we have again the options: 4 carbons or 6 carbons. So let's see how many chiral carbons are there, which we know that it is that carbon which is bonded with 4 different groups. So all those containing the double bond, they are removed, they are ignored, and all those containing 2 hydrogen atoms on them, they are also ignored. So let's check the remaining carbon atoms. Here is the one asterisk. This asterisk indicates the chiral carbon. Another chiral carbon is present here, and then another chiral carbon is present here. Now, we have these 4 different types of the these were the 3 chiral carbons. Now this one as well. This is 4th one. This is the 5th one. And this is the 6th one. So in total, we have these 6 chiral carbon atoms present in this compound. So the right option should become 6 chiral carbon atoms here, which means option C and D. And the option D contains both the ticks here. So that's why the correct option becomes option D of question number 36. Now, question number 37. A molecule of hexane can be cracked in a number of different ways, and the compounds are listed. Which compounds are found in the mixture products from the cracking of hexane molecules? All right, here we have to decide the fragments or the fractions which are produced by the cracking of hexane. Hexane, as we know, is an alkene compound with 6 carbon atoms. Now, this first compound is basically the propane. The second compound is basically butene. And the third compound is pentane. Now, if it is hexane, then hexane conversion to pentane is of no use. It's just 1 carbon less. So 1 carbon less has no such significance in case of the cracking. So that means it should not be the product in case of cracking, but 1 and 2 should be the products, because these are 4 carbon atom chains. This is sorry, 3 carbon atom chains, and this is 4 carbon atom chains. So these are of difference as compared to C6, having 6 in the hexane. So option B is considered to be the correct option. Option B. Now, question number 38. Question 38 says the diagrams show the structure of two isomer dicarboxylic acids X and Y. And X can be reduced to compound P with this empirical formula. Y can be reduced to compound K with this empirical formula. This statement is correct. Okay, so here we have to discuss the type of the compound X is showing, like the which kind of isomer is it, and then the product formed as a result of the reduction of X and Y, and what are their types. So let's see the first part that says X is a cis isomer or is it a trans isomer. So we can see here that there are two hydrogen atoms on one side of this carbon-carbon double bond, and then we have four carboxylic groups on the other side of the carbon-carbon double bond. So this type of the structure indicates the cis type, since both hydrogens are same on one side and both carboxylic groups are on the other side of the carbon-carbon double bond. So this is cis. So from here, the correct option becomes the cis isomer. It is not trans isomer. Now the second part says that we have to see compound P and Q, and then the types of these two compounds P and Q. So for this purpose, it says that they were reduced. Both X and Y were reduced, and we know that X and Y have similar number of the carbon atoms, hydrogen atoms, and oxygen, as well as the functional groups are also same in both of these compounds. So by reduction, we can consider that the carboxylic group can be converted into the CH2OH part, and this C also can convert into CH2OH. This is reduction, the reduction of carboxylic group into the alcoholic group. And at the same time, the carbon-carbon double bond can also be reduced, but this time it should be considered as an alkene part converting into the alkane part. This is also reduction because hydrogen atoms, one hydrogen atom can go on this carbon and another hydrogen atom can go on this carbon. So this is also reduction. Okay, we can now consider two options here. The first option is that we consider that the carbon atoms of the alkene are not, basically, they are not reduced. So which means only the carboxylic groups are reduced. So here we will have this case now. CH2OH bonded with the CH double bond CH, which is further bonded with CH2OH because the carboxylic groups are considered to be reduced. Now we have to count the number of carbon atoms and hydrogen atoms because from there we'll find the empirical formula. So in total we have 4 carbon atoms and hydrogen atoms. Let's see how many are there. 2, 4, 6, and 8. One over here, one over here. So there are 8 hydrogen atoms and oxygen atoms, there are 2. Now this is the molecular formula. We convert this molecular formula into the empirical formula. So empirical formula becomes C2H4 and O. This is empirical formula, but this empirical formula does not match with this empirical formula C2H5O. So this is not the type of correct reduction, which means we need to include the reduction of the alkene part as well. So one hydrogen will go over here and one hydrogen atom will go over here, and this current is single bond. So we will say that it should be CH2 and it should be CH2 here and double single bond here, which means we have just increased 2 hydrogen atoms more as compared to the previous case, which means we will add now 2 hydrogen atoms here. So it should become C4H10 and O2. The rest will remain the same because carbon and oxygen atoms are not changed. Now, the empirical formula of this will be, if we divide with 2, you get C2H5 and O. So C2H5 and O is formed, which is matching with this formula C2H5O. So which means that the alkene part was also reduced. Now, if this is reduced to compound P, then Q is formed from compound Y, which also has similar functional groups, 2 carboxylic groups and 1 alkene part, which means this will also give a similar compound, just like a compound P having similar molecular formula. and this will convert it into a single bond. Now, what options are given here? That compound P and Q are identical. So yes, they are identical. What for P and Q are isomers of each other? P and Q could only be isomer if the alkene part was not reduced. If it was still there, then we could have cis and trans. But since they are reduced into alkane part, then alkene cannot give cis trans isomer. And we cannot have any other type of the isomerism. So yes, they are identical, which means that correct option A is the correct answer. Now question number 39. What is the total number of sp3 hybridized atomic orbitals used in the bonding of butene? Okay, so which means we need to understand the structure of butene. It is like this. In a simplified form, there are 4 carbon atoms with a double bond at position number 2. Okay, so here we can simply see that the carbon atom which are present in the double bond, they are sp2 hybridized. As we know from the literature that whenever carbon form the double bond, it will be in the sp2 form. But the carbon atom on the either side, they are sp3. This one is sp3 carbon, and this one is also sp3 carbon. These are the identified hybridized states of the carbon atoms. Now we see how many of the sp3 hybridized atomic orbitals are there. We have to count the number of atomic orbitals. So which means we need to elaborate this structure into its complete form. We know that carbon, the butene structure is like this. The carbon bonded with the hydrogen over here, and then carbon, double bonded carbon, one hydrogen here, another hydrogen here, carbon, hydrogen, and hydrogen. Now, since we have assigned that the left and the right, the far left and far right carbon atom are sp3 hybridized, which means the number of bondings will indicate the total number of hybridized orbitals. So this is sp3 hybridized atomic orbital of carbon. This is also sp3 hybridized atomic orbital of carbon. This one is also because they are used to make overlapping with the s orbitals of the hydrogen atoms. All the hydrogen atoms have the s orbital. So these kind of sp3 to s overlapping in the bonding. Similarly, one more, okay, 3 from here. So they are now 6. And additional, there is another bonding between carbon of double bond and the sp3 carbon. These two carbons, the type of bonding over here will be sp3 atomic orbital bonded with the sp2 of the carbon-carbon double bond, because this was sp2 atomic orbital hybridized. So one sp3 is present here and another one sp3 is present here. So previously we had 3, we had 6, and now additionally we have 2 more. So in total we would have 8. 3 plus 3, 1 plus 1. So total we have 8. So that's why the correct option becomes D option. Now the last question, number 14. Compound L contains carbon atom. It is analyzed in mass spectrometer. The table is given with only 2 peaks with M by E value greater than 127. We have to determine the number of carbon atoms present in one molecule of compound L. All right, so here we are given M by E values and the relative abundance. So the formula to find the number of carbon atoms from the values of the relative abundance of M plus peak and M plus 1 peak, M plus peak, and then M plus 1 peak. The formula used is given in the syllabus, and that is this formula. N is equal to 100 into abundance of M plus 1 ion divided by 1.1 into abundance of M plus 1 ion, M plus ion. Now we have to determine which of these are M plus 1 and which is the M plus peak. So this is 128 and it's 129. So we can consider that this 128 is basically the actual molecular ion peak. So molecular ion is basically the M plus peak. And this is one value greater than 120, which means this is indicating the M plus 1 peak. So this is M plus 1 peak. Okay, so these are the relative abundances. So we now apply the formula. N is equal to 100 in numerator, 1.1 denominator into relative abundance of M plus 1 peak divided by relative abundance of M plus peak. So we apply this formula. Now put the values. Now the value will be 100 over 1.1, and abundance of M plus 1 is basically this is M plus 1 peak. So 5.5 divided by M plus peak, which is 50. Okay. Now when you compute this value in calculator, you will get a value of 10, and that's why the actual answer, the correct answer is option D. Now in this way, we have completed this paper of 5 March 2025, paper 1-2, and I hope I have clarified all the queries. You can reach me out for topicals, solved and unsolved, and you can also get the ES chemistry notes of the whole syllabus as well as A2 chemistry notes and their topicals. So I will come back with another video on past papers of the recent years. Till then, you're welcome to send any questions in the comment section. So till then, take care and bye bye everyone.